So segment 2 of chapter 5. So in the last segment we left off with calculating oxidation numbers, and now we're going to start to look at reactions and take advantage of those oxidation number changes in order to understand what's going on in the oxidation and reduction reaction. So we're going to redefine the oxidation reduction in terms of oxidation numbers, right? So we looked at oil rig, oxidation is loss, reduction is gain. So we know that there's going to be a change in electrons, but now we're going to look at it in terms of oxidation numbers. So a redox reaction occurs when there is a change in the oxidation number. So for oxidation, we're going to see an increase in oxidation number. That means we've lost those electrons. For the reduction, we're going to see a decrease in the oxidation number. In other words, we're going to gain electrons. So using the oxidation numbers to recognize redox reactions, so sometimes literal electron transfer, in other words, if we take a copper 2+, we add zinc, and then of course the zinc becomes a zinc 2+, and we form copper metal, then what we're actually going to see is a decrease in the reduction, right? So we went from +2, we went to 0, right? So that's my reduction. And then we also went from 0 to +2, and that's going to be our oxidation. So copper then, oxidation number decreased by 2. That's going to be reduction. It was reduced. It reduced from 2 to 0. The zinc, the oxidation number went up, and so we call that oxidation. Right? So reduction and oxidation can be deduced from changes in the oxidation numbers. So here we have CH4 plus 2O2 going to CO2 plus H2O. So this is our standard combustion reaction. So we're going to burn some methane. And then if we look at the numbers here, we know that since oxygen's in its elemental state, that's going to be a 0. Here, it's going to be a -2. It's also going to be a -2 in water, right? So remember, neither one of these are peroxides, so the oxygens have to go to -2. For the methane, we know that hydrogen's always a +1. So there it is, +1. That means the carbon then has to be a -4. Now, that might seem a little odd because we saw a case where carbon was a +4, and here it is over here, it's a +4. Okay, so carbon's going to go from -4 to +4. Now, for the carbon then, we get an increase in the oxidation number, right? We gained 8 electrons is the way that's going to look. And so that's going to be oxidation. For the oxygen, it went from 0 to -2 on both of these. That's going to be a reduction. Now, what about hydrogen? Well, hydrogen stayed as a +1 throughout the reaction. Okay, so nothing happened there. Oxidation number then for oxygen decreases by 2. That's going to be reduction. Carbon, it went from -4 to +4. So that's going to be an increase of 8, and that's going to be our oxidation. All right, so your turn then. Assign oxidation numbers to all atoms in the following reaction and use them to determine which species gets reduced. All right, so assign oxidation numbers to all the atoms, and then we're going to look at which one has been reduced. So here we know that oxygen has to be a -2. Now I'm not going to worry about the coefficients when I'm looking at oxidation numbers. So this 2 out here in front, we don't care about that thing. All we care about is the molecule itself. And so here we have a -2 for oxygen. That's going to be a total of -6, right? Because we have 3 of them. Now our overall charge needs to be a -2, which means really we have a -4 for our oxygens. We have 2 sulfurs. They have to sum up to be a +4 so that we can balance out that -4 to have an overall of -2. That means each sulfur then here must be +2. Now I3-, this is not its elemental state. It is an overall -1 charge, which means this is going to be what? -1/3. Okay. Now, in our product side, we have oxygen here is going to be a -2. This time we have 6 of them. It's going to be -12. We need to have an overall -2 charge. That means we need to deal with -10. And this time we have sulfur being a 4 that has to be +10. that means the S4 then has to be plus 2.5, 2.5 or 5 halves. And then out here, we have the 3 again is not going to matter. So the iodine is now -1. So we have sulfur overall went from +2 to +2.5. We have iodine went from -0.33 to -1. So we can see here iodine was reduced, sulfur was oxidized. So our options are I3 minus, I minus, S4062 minus, S2O3 2 minus. And of course we're going to say the I3 is what was reduced. All right, so again, I erase my red here. You can see they're showing us the same thing, right? We can see that we got it exactly right. All right. Iodine was reduced. It went from -1/3 to -1. All right, so the next thing we want to look at is the ion-electron method. This is going to be a method used to balance redox equations. Now, you must balance both the mass and the charge. So just like a standard reaction, we're going to start with that skeleton equation, right? So we're not going to have any coefficients. We're only going to have ions and molecules involved in the reaction. And what we're going to do is we're going to break it into 2 half reactions. We're going to break it into the oxidation half, and then we're going to break it into the reduction half. Then we're going to balance each half reaction separately. So in other words, we're not going to try to figure out all the electron movement between both the oxidation and reduction. That can sometimes get very complex. So far, the ones we've looked at, pretty simple. You might be able to go ahead and do that, but obviously I'm going to start to give you ones that are a little more complex. It won't be so straightforward. So what we'll do is we'll balance each half reaction separately, then combine them to get the final net ionic equation. And of course, it'll be balanced both by mass and by charge. So balancing redox reactions, some redox reactions are very simple, right? We saw this one already. We looked at copper with a +2 charge. We add some zinc solid, and then we're going to get copper solid out of that and zinc 2+. Typically, we would have done this reaction in the lab in a normal semester. So hopefully you were able to do that on a norm. I know this semester we were not. We'll break this reaction into half reactions. Now we can see that it's a 2 electron transfer. So realistically, we could probably balance this fairly quickly without having to do anything else to it. But what we're going to do is we're going to look at the half reactions. So zinc here as a solid is going to go to zinc 2+ plus 2 electrons. And of course we know that's oxidation. And that means the zinc here is going to be our reducing agent. Copper 2+ plus 2 electrons is going to give us copper solid. That's going to be reduction. And of course the copper 2+ is our oxidizing agent. Now notice that in these reactions, I have electrons on the product side, and then I have electrons on the reactant side. So the reducing agent always has electrons on the product side, and the oxidizing agent always has electrons on the reactant side. You can never have electrons both on both on the product side. If so, then you've messed up one of your half reactions. Okay, you can't have electrons, they both can't have electrons on the reactant side either for the same reason. So if you break it into 2 half reactions, one way you can check yourself is to make sure you have electrons on the products for one half and on the reactant side for the other half. So when we look at the oxidation side and we look at the reduction side, we know that each half reaction is now going to be balanced for atoms, right? So I have 1 copper, 1 zinc, 1 zinc. Same number of atoms, each type on each side. Now we didn't worry about electrons. Okay, that's going to come when we put them back together. Each half reaction is then going to be balanced for charge. So we're not going to worry about the electrons by themselves. We're going to look at the charge. So what we're going to do for that is say, okay, here's zinc, and over here it's a 0. There's no charge. On the product side, we have a +2 plus 2 times a -1. That's also going to be neutral, right? So now it's mass balanced because we have zinc on both sides, and it's charge balanced because both sides are going to be 0 charge, okay? We could do the same thing for the copper reaction. So we have the same sum of charges on each side. Now what we're going to do is add both equations algebraically, canceling out the electrons. Okay, so when you finish your net ionic equation, you can never have electrons left over. Now this one's pretty straightforward because it's 2 to 2. But you can imagine if I had 3 electrons over here, then what I'm going to have to do is multiply these equations out algebraically to get the 2 and the 3 to cancel. And of course, that common factor would be 6. So we'd multiply this reaction by 2, we'd multiply this reaction by 3, and that way we've got 6 electrons on each side here. The electrons would cancel out, and we'd simply sum up the remainder of the pieces. All right. So balancing redox equations and aqueous solutions then, many redox reactions and aqueous solutions are going to involve water. And that means water is always going to have H plus and OH minus. And of course, you know there's going to be water there because it's called an aqueous solution. We've already seen that in solutions chapter. We know that that means there's going to be water around. Balancing the equation cannot be done by inspection. So the more complex these reactions get, then you won't be able to just look at it and know, I'm going to put a 2 here and I'm going to put a 3 there, and it's just going to balance out. So if you've been practicing balancing, you might have gotten real good at balancing by inspection. Typically, that's not going to be the way these are going to work out. So you're going to need a method in order to balance it. So what we're going to do is we're going to start with an acidic solution and then work to basic conditions. Okay, so we're always going to say we're in an acidic solution. When we go to look at basic solutions, you're still going to be solving with an acidic solution format. All right, and you'll see this as we go through. I'll point it out again. So an ion electron method with an acidic solution, we're going to divide into the equation into 2 half reactions. And now we're going to balance our atoms other than hydrogen and oxygen. Then we'll balance oxygen by adding water to the side that needs oxygen. Now that means we might end up with some extra hydrogen, right? And if we do, we'll balance the hydrogen by adding H+. Now remember, it's an acidic solution, so that's going to be fine that we have H+ left over. Then we're going to balance the net charge by adding the electrons. Okay, so using the H pluses and the waters and the overall charges, that's going to tell us how many electrons we're going to need to exchange out of there. Then we'll make the electron gain equal to our electron loss. That's where we're going to multiply each equation if we need to. And then we're going to bring those 2 half reactions together. And bringing them together, we know that the electrons should cancel out, and then anything else that's able to cancel out, we will. So like if we end up with 5 waters on one half and 2 waters on the other, we'll cancel that out so that the 2 waters go away and we're left with 3 on the one half. So redox equations then. Example number 2, we're going to mix solutions of K2 potassium dichromate and iron 2 sulfate. Okay, now the dichromate ion, Cr2O2- O7 2- oxidizes iron 2+ to iron 3+. Okay, the dichromate itself will be reduced to form a chromium 3+. So in that, and actually we saw this, right, because we had a bad calculation. We know that in this, the chromate is actually a +6, right? We saw that miscalculation earlier that stumped Mr. Caro, I believe in segment 1, where I was shaking my head at going, wait a minute, something's wrong, and then we went in and fixed it with the red pen. And that's because the dichromate should be a +6. And we know we're going to reduce that to chromium to +3. Now the acidity of the mixture decreases as H+ reacts with oxygen to form water. So when we first mix these together, what that's telling us is that the solution is going to be acidic, but as the reaction takes place, the hydrogen plus the acidic hydrogens are going to be forming water. Okay? So your skeleton equation then is going to be dichromate plus iron goes to iron 3 plus iron, chromate 3 plus iron 3. All right. Now, balance an acidic solution then, Cr2O7 2- plus Fe2+ goes to chromium 3+ plus Fe3+. No, I know what you're saying. Well, wait a minute, what happened to potassium? So if I go back, you can see potassium was originally in there. Same with the sulfate. These are just going to be ions in solution. They're called spectator ions. You might want to go back and look at solutions on how that happened. We won't worry about them. Okay, so they're not going to impact the oxidation reduction portion. They did not just disappear though. They're just in the solution as spectators, and so we isolate them. We don't care about them. All right, so the first thing we're supposed to do after we have our skeleton equation, and typically on an exam, I'm going to give you that skeleton equation, but you're going to have to break it into the two half reactions. So the first reaction we know is the chromium going to chromium, right? So there's the dichromate going to chromium 3 plus. The second half reaction is going to be just simply the irons, Fe2 going to Fe3, okay? So there's my two halves. Now, the first thing we want to do in each half is balance the atoms other than the hydrogen and the oxygen. So in other words, if you look at that first half, you have dichromate going to chromium 3 plus. Okay, so that means I'm going to need to form two Cr3 pluses. So for every dichromate that reacts, I'm going to make two chromiums turn to 3 plus. So we're going to put in the 2 coefficient to balance out the chromiums. For the irons, we don't have to do anything. They're going to be 1 to 1. It's already balanced. Nothing to worry about there. Okay, remember, we're not worried about the charges yet. That sometimes gets a little confusing, but iron is iron. Doesn't matter what its oxidation state is. Every iron would be a single iron. Next, we're going to balance out the oxygens by adding water to the side that needs oxygen. So we're going to go back and look at this dichromate going to 2 Cr3 plus. Since we can see we have 7 oxygens on the left side, then what we're going to have to do is add some to the right side. The way we're going to do that is by adding waters. So we're going to add 7 waters to the product side. That's going to give me my 7 oxygens. Okay. Now for the iron, there was no oxygen, so we don't have to do anything. No oxygens to balance, which means we don't add any waters. All right, the next thing we want to do then is balance the hydrogen by adding H plus to the side that needs hydrogen. So again, looking at that dichromate half, we just added 7 waters. Well, that means on the right side, we have 14 hydrogen. On the left side, we have none. So we're going to add 14 H pluses to the left side. I know this seems crazy. Trust me, it's all going to work out at the end. Okay, so this method is going to work every single time. For the iron, again, no oxygen, no hydrogen, nothing to add. Don't have to worry about it. All right. The next thing we're going to do now is balance the net charge by adding the electrons. So we've added our oxygens as waters. We've added our hydrogens to balance the hydrogens from the waters. Now we're going to look at charge. So for the net charge here, we're going to have 14 H pluses. That's a plus 14. We have 1 dichromate. That's going to be a negative 2. So on the reactant half then, we have 12, right? 14 times 1 minus 2 gives me 12. So we have a plus 12 charge. On the other side of the reaction, we have 2 times 3 plus 0. So that means we're going to have a total of 6. So the net charge on the product side is then 6. Now we have to charge balance this. So that means in order to make the plus 6 and the plus 12 equal, I'm going to have to add electrons. So which side should I add the electrons to? Well, I need to bring the 12 down to 6. So I'm going to add 6 electrons to the reactant side. Okay, so 6 electrons are added to the reactant side, and that's going to be it for that half. That half is now completely balanced both by mass and by charge. Now, the other half of the reaction, iron 2 going to iron 3, we didn't have to add water, we didn't have to add hydrogen, which means now we just want to look at the charges. And so we have plus 2 on the reactant side, plus 3 on the product side, and so we're going to have to add 1 electron to the product side to make that balance. Now, the individual half reactions are balanced. The overall reaction, the net ionic reaction, not balanced yet. All right, so we have the 2 halves done. Now what we have to do is make those electrons work out for us. So here are our 2 halves. What I'm going to need to do is get 6 electrons on both sides in this case, because we have 6 to 1. So we're going to multiply the second half reaction by 6. Now that 6 is going to carry through the whole reaction. So we're going to end up with 6 iron 2 pluses and 6 iron 3 pluses. But from that, we'll get our 6 electrons to balance with the first half of the reaction. At this point, we can sum it up. On the reactant side here, we have 6 electrons now. We'll now have 6 times Fe2 plus. We have our 14 hydrogens and our dichromate. So all of that came down to the product side. Excuse me, to the reactant side. On the product side, we have the 6 times the Fe3 plus. We have the 2 chromates, 3 plus, the 7 waters, and then of course 6 times 1, so 6 electrons. Now what we're going to do is cancel out everything that's the same on both sides. So obviously the whole reason why we did that was to cancel out the electrons. If there's anything else that can cancel out at this point, we would. However, nothing else is going to cancel. Don't be tempted by the irons. They're 2 different irons, right? They're +2 and +3, so they do not cancel out. At this point, we would rewrite the whole reaction and give us our final reaction. So 6 Fe2 plus 14H plus Cr2O72 minus 6 produces 6 Fe3 plus 2 chromium plus 3s and 7 waters. All right, and of course when we started this out, we said the acid was going to turn to water as it went, and there it is. All right, the next thing we're going to do is look at this in basic solution. But again, I like to keep these segments to 20 minutes or less, and we're already at the 21-minute mark. So we're going to start the next segment off with doing that same reaction, but in basic solution. All right, so the same style of reaction, but in basic solution. So we're just going to add a few steps.